Conference season is upon us, and you're probably preparing plots for your poster or for your talk. So this week we're going to talk about color maps and how to choose the best one for your data. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. On this week's MetPy Monday, I want to stray a little bit from what we normally talk about, which is how to make your code better, and talk about how to make your presentation of your data better through your code. And that's with color maps. So you'll probably make color mapped plots for any presentation that you give. We're always shading things like temperature or topography or pressure or relative humidity, and we have to choose a color map to do this. And all color maps are somewhat imperfect because the human visual system is pretty complicated. There was a really great talk at SciPy several years ago on this topic. There's also been some work out in the literature, such as rainbow color map still considered harmful from IEEE Computer Graphics and Applications back in 2007. Instead of going into the detail on how color maps and your eye work, because that's been done so much better than I could in some of these talks and papers, I want to just show you a couple things about choosing a color map. First of all, go look in the Matplotlib documentation at all these color maps that are available to you. You can read about them, but also keep scrolling, which a lot of people don't do, and look at these plots of lightness. Lightness is a proxy value that we can use to determine what change our eye sees in these color maps. So if we have a color map like Viridis here, where the lightness changes linearly with change in value, then we can roughly say, well, if I go from 50 to 100, my eye perceives a change of that magnitude, which is the same as from 100 to 150. So the straight lines for sequential color maps, or color maps that go from one value to another, are great. These are really useful for continuous quantities like temperature or relative humidity. In a similar vein, there are some of these other sequential color maps that aren't perceptually uniform, but they're not too bad. You see, we've got a little bit of curvature, so there's some change in how your eye perceives things, but it's not too bad, and they're mostly linear. Greens, for example, or yellow-green, are pretty common color maps that we use for things like moisture. Another type of plot that you might want to make is a difference from a mean. So we might be wanting to show temperature anomalies, pressure anomalies. Maybe you want to show hot and cold air advection, which are small quantities around the roughly mean zero quantity. In that case, you're probably looking for a divergent color map. So divergent color maps, we want to see them start at their highest lightness value and linearly go down from it with different hues. So, for example, a red-blue color map is one of my favorite choices for these. A seismic color map, though it looks very similar to a red-blue, as you see, has several kinks and discontinuities that make it not quite as good of a choice, even compared to something like blue-warm. So have a scroll through all of these lightness plots and check your color map. If you're using something like cool, you might say, oh, well, that's actually not very perceptually linear. There are the qualitative and repeating color maps, which I'm not going to cover in this video, but I want to show some of the miscellaneous color maps that we do see a lot in plots at conferences. Rainbow and jet being the main offenders. As I mentioned earlier, these are very nonlinear. Even GNU plot is pretty nonlinear. GNU plot 2 is somewhat better. But I don't really recommend using any of these color maps, and I'm going to show you why. Another factor to consider is what's the standard in your field. For example, CM Ocean is a set of color maps that the oceanographic community has gathered around and said, we want to use these color maps for quantities like dissolved oxygen or sea surface temperature. So you should check in your community, but just because it is what most people in your community use might not mean it's the best choice if it's something like jet. But it's something to keep in mind, is what are your attendees or your audience expecting to see your data presented in? And always go look at MetPy's color maps as well. Now, I can already hear you saying these are not very perceptually uniform, and you're correct. But for things like the IR color maps, these different discontinuities have physical quantities associated with them, actual physical meaning. So there's a reason that the color maps like that. So those are also available for your use. But let's hop into JupyterLab and write a little bit of code. So I'm going to import NumPy as MP, import matplotlib.pyplot as PLT, and I'm going to use my matplotlib inline magic, so my figures show up in the notebook. I'm going to use the meshGrid function from NumPy to create a two-dimensional array of numbers to evaluate a function on. In this case, it's a function that takes x and y, returns a z value, and it's going to be the Ackley function. The Ackley function is a great function for testing optimization algorithms on because it has many local minima and one global minima at 0, 0, 0. The equation for it shown here, it's not that complicated, it's just a lot of terms. But this is a great function because you can see here it's presented in the jet color map, and all of these little ridges here are completely washed out in the color map. So we're going to plot this in 2D and test it with some different color maps to see what I mean when I say it's perceptually non-uniform. All right, so I'm going to use NumPy's meshGrid. I'm going to unpack the three-dimensional array into two two-dimensional arrays. That's just a little bit more intuitive to work with here. And I'm going to have my x's be linspace between -4 and 4 with 100 points. And I'm going to have my y's be linspace between -4 and 4, also with 100 points. But in meteorology, we might have many more points in longitude versus latitude if we're doing something over CONUS, for example. So if I look at the shape of x, I expect it to be 100 by 100, and that is indeed what I get. Looking at x, I see that the rows, if you will, the inner dimension, go from -4 to 4. Okay, so now I'm going to code up the Ackley function for you. I encourage you to go do this on your own. Just take a look at that equation and code it up, and then come back and compare with what I've got. All right, so there's my Ackley function. The main thing to notice is that I used parentheses to avoid using line continuation characters when I did my line wrapping. And I'm using things like np.py and np.e for physical constants instead of typing in approximations. All right, so now let's compute the Ackley function over our grid, x and y. That ran very fast. Again, remember to use this, not looping. It's a lot faster. And if you actually do go ahead and do the experiment of writing a loop for I in row, for j in column, you'll find out that it's about 3 orders of magnitude speed difference here. But let's go ahead and make our plot. So fig and x is plot.subplots. I'm going to make a contour f, or filled contour, of x, y, and my z values. And I'm going to set the aspect ratio of my plot to be equal. So now I get a plot where each of these 0 to -4, 0 to -4 is the same distance on the figure. I'm going to go ahead and add some more contours, maybe 1,000 levels, which will take a little bit longer to run, but there we go. So the default is the Viridis color map, which I think is really pretty sensible. And we see a grid, basically, of these little local minima, descending, descending, descending until we get to our global minima at 0, 0, 0. We can go ahead and add a color bar if we want. I'm going to grab a handle to those contours and then call fig.colorbar and pass it that handle. It's always nice to provide a reference. Okay, so there's our color bar. So now if I go ahead and change the color map, let's do something like jet. So that looks pretty bad. There's a big disconformity or unconformity, if you will, in how I see the image right here and right here. So that's sort of in the yellow, the red to yellow transition and the green to blue transition. So if I go back and look, the green, blue, red, yellow, those are up here when jet is turning around in lightness space. So that's exactly what I would expect. And really, it's very hard for me to tell that there are minima some places, these local minima. It's just a pretty deceiving color map. If I look at something like the rainbow color map, we'll see it's actually even worse. We have some very weird artifacts here that look completely bizarre, as well as this big visual artifact out here, again, at the blue-green transition. So those are some bad color maps. But Viridis is a pretty good choice. Plasma is another very good choice. It is perceptually uniform as well. So we get the same look as Viridis. Greens are also, it's not quite perceptually uniform. So if we go back up here and look, that's a capital G greens, or yellow green, YLGN, that's another common one. Yeah, so we still get a pretty good idea. I don't see these artifacts out in this area. So choosing a color map can make a very big difference. Now, a divergent color map doesn't make a ton of sense for this data set, but I want to show you one anyway. So we'll do red-blue, or RDBU. RDBU. So here we are going to see a difference because we have the mean value, if you will, which in this case is about 6, being this white color, but I can still see all of the minima. So I'm not having near as much problem as I did with jet or rainbow. So the moral of the story of this MetPy Monday is do justice to your data. You've worked hard to produce it or hard to collect it, and you shouldn't be tricked by visual artifacts, by the fact that our eye is complicated and data are complicated and computer graphics are complicated. So you want to make sure that you're fair to your data, to yourself, and to the viewers of your presentation. We'll continue on this data trend by soon talking about how to take some model data, very recent model output data, and make plots that we might care about of what's a forecast of a point or of a grid, and how can I visualize that on things like CartaPy maps or multi-figure plots. So I hope that you found this useful, and I'll see you on next week's MetPy Monday.